Hello, my name is Colin and I'm in Group 13 with Ahmed, Jose, and Jacob, and our project is on a smart, compact hunting scope. My main role in the group was handling the optics as well as the housing for the system. We have Ahmed as a computer engineer. He was dealing with the application as well as implementation on the display. We had Jacob in charge of the PCB and the microcontroller and its integration with the rangefinder and the OLED display, and we had Jose in charge of power distribution for the entire system.
Hi, my name is Ahmed Saidi and I'm the computer engineer of Group 13's LPVO project. One of our main goal of our project was to create a scope design that will account for the bullet trajectory. A couple of our objectives were to be able to blaze up to 1,000 meters, have a transparent OLED display with a lot of features such as displaying the range, displaying the pixel, and much more, as well as having a complete custom PCB design that allows us to do all of the following.
Hi, my name is Jacob Clevenger. I was responsible for designing the PCB of this project with the help of Jose. My part was to integrate the microcontroller onto the board, as well as the display and the rangefinder. The biggest lesson I learned in this project was about how to design a PCB and carefully placing your components, as well as making sure they're the right component. So through-hole components should all be through-hole, while the surface mount, you should make sure our surface mount design.
Hello, my name is Jose Vasquez and part of Group 13. What I'm going to be talking about is the impact of this project that it had to society as well to the broader impact. So this project is really pushing the limits and the innovation that scopes in general can have in the military space and also in the hunting space. As well, the second point is that this project is going to target one of the biggest goals and objectives that we have is that it's going to be really time efficient for the hunter or soldier that's going to be using it to aim and target at their target and successfully hit it every time.
Jose, my part was to integrate the microcontroller onto the board, as well as the display and the rangefinder. The biggest lesson I learned in this project was about how to design a PCB and carefully placing your components, as well as making sure they're the right component. So through-hole components should all be through-hole, while the surface mount, you should make sure our surface mount design.
Hi, I'm the computer engineer for this project, and my role in this project was the software engineer, essentially. I built the microcontroller program as well as the app design. Part of the reason why we needed a program to make this work is because there were a ton of features that we decided to implement, including the contrast, displaying various aspects onto the display, as well as having a mobile attachment so that you can have all of these features on the go on your mobile phone. Currently, the application only works on your Android device, but we have future plans to port it over to iOS, as well as have a website that will let you do the following.
The photonics major for this group project. The main reason why we needed a photonics major was for implementation of the scope. We did need to have multiple optics to allow for the sight picture for the user, as well as a housing that would encase all the optics as well as all the electronics. For this project, I had to teach myself a bit more about how a magnified system works. So we ended up using a much larger and more complex optic system than I have been previously shown, as well as having to learn CAD components so that way we can make a housing that holds everything in, but still able to be robust and compact.
Hello, I'm the electrical engineer of the project, and what I worked on was the power supply and the USB to I2C interface. What I should have done when it comes to the power supply is that when we first designed it, we used multiple batteries, and one that is bad for weight, space, and it was inefficient. So we should have accounted for voltage regulators right from the start, but that came out afterwards, and we realized that was the best design.
I'm back again as a software engineer, and a couple of things that I learned during this project is I learned that a lot of programs at the very low level require a lot of specific functions and iterations, such as interrupts, and using a lot of different very low-level data structures, such as a character array, versus using a string object. Amongst that, I learned that a lot of the functions that our project required was very new and has never been done before. Therefore, that motivated us so we can extend that industry and prove that things can be innovated in that space, as well as that motivated us to perform better than anything we've seen before.
One of the biggest challenges that we had during our planning is that the microchip for the USB to SPI interface became out of stock by the time we were ready to order it. So what we had to do is that we had to use the existing schematic that we had in the new microchip and implement it into it. And we had to adapt with the microchip's different schematics and our existing schematic to make it successful and work.
This is a part of the scope that will be mounted onto the rifle. In it is the PCB that we designed with the microcontroller and the USB interface. On the front of it is a display that will be mounted into the scope housing. This is a rangefinder that we will mount to the side of the mount. And this will be wired into our PCB along with power on the other side of the scope mount. And that will be the electrical part of this project.
My main focus in the project was to cover the optical system as well as the housing. So for this main section, the larger tube is going to be the eyepiece. This is what houses both lenses of the eyepiece as well as the magnifying lens to give a magnified picture. And the smaller section is what's going to house the objective lens as well as the reticle. So this box is where the OLED display is going to be entered into, so that way it falls into an image plane that the user is able to see. The user will be on this side with a collimated beam coming in from the far side, and this is where the user is going to be able to see their picture with the reticle overlaid.